You start at the top, and what you do is you measure how much daughter and how much parent is in the rock. Now see, you might have this one basalt lava flow, okay? And you get 4 or 5 samples from it. Now, these samples, because of the random distribution of atoms, and remember, rubidium is a trace element. So in one sample you might have 100 parts per million, in another sample you might only have 5 parts per million. But that's good for this method because 100 parts per million of rubidium, or say 1% of rubidium, will produce more strontium than 0.1% of rubidium. Okay, it'll produce less strontium. And so what happens is when you plot the parent on the horizontal versus the daughter on the vertical, you actually get the data points spread out on that graph. And you want them spread out because what you're doing is you're trying to fit a line through those data points, the line of best fit. And the more spread out they are, the better, because you'll have, as the statisticians will tell you, you'll get better fit statistics to your line of best fit. And I can see a few people nodding there because you're obviously mathematicians or done mathematicians in your technical work. So, how does this give us an age? Well, go to the middle graph. Okay, when the rock formed, different samples from this lava flow have different amounts of rubidium in them, but they all have the same, the theory says they all have the same strontium starting composition. Okay? And so with time, so they plot as a horizontal line. Different amounts of rubidium as you go from left to right, greater amount of parent as you go from left to right, but the same amount of strontium. Okay, now as the clock ticks away, the sample with the greatest amount of rubidium is going to produce the greater amount of strontium. Less rubidium, less strontium. So that line actually tilts up, it pivots on the zero, from that 0 point, okay? From the starting point, it actually pivots. And so the older the rock, the steeper the slope of that line. And that line is called the isochron, which means same age. It connects all those rocks, those samples, because it's from the one lava flow which erupted at the same time from a volcano. Okay, so the age of the rock should all be the same, but these plot at different points, and yet a line fits through them. The slope of that line, which is called the isochron line, actually is the age of the rock. So the steeper the slope, the older the rock. 0 age, horizontal, no slope. And so that's what we mean by an isochron. Okay. Now, for those of you who that was too technical for, okay, that's fine. Now you can switch back on again. And we'll get back to something a little bit more simple. But I wanted to explain that for those of you who are more technically minded. Because when we did this work, we chose to usually use the superior isochron method, and instead of using 4 or 5 samples, we went for overkill. And the reason why we went for overkill in using more samples than geologists would normally use is we wanted to make the point. In other words, we want our results to stick and not be challenged. So how reliable is these radioisotope dating methods? Well, let's remember assumption number 1, all the daughter atoms were derived from the parent atoms by radioactive decay. Assumption number 2, no other process has affected the parent-daughter relationship through time apart from radioactive decay. And number 3, the rate of decay has been constant. Okay, let's examine each of these 3 assumptions. Let's go to the Grand Canyon. Why not? The Grand Canyon is one of the best known places. It's in every geology textbook. It's in every tourist brochure, every tourist flyer. And there's some lava flows there in the western Grand Canyon that are so recent, you can see the craters still, the volcanic cones still on the north rim of the Grand Canyon, and the lava's trickled down the walls of the Grand Canyon after the Colorado River had carved out the canyon. And you can see some of these, see this cone there, and you can see some of the lavas pinned to the wall, like this one here. You can actually see where it flowed from the rim right down to the river. Some of these lava flows actually blocked the Colorado River and dammed it up temporarily before the water burst through and eroded out the basalt. And some of these lava flows actually flowed down the Colorado River. So how old are these lava flows in the Grand Canyon? They're so recent, by the way, there's some evidence that the more recent eruptions may have even been witnessed by the Native Americans. So they give potassium argon single sample model ages from 443,000 years all the way up to just over 1 million years. Okay, that's comparing two rock samples. We also extracted a mineral, the green mineral olivine, from which we get our gem mineral called peridot. Some of you might have heard of peridot. It's a gem variety of olivine. From these same two rock samples that give potassium argon ages, the whole rock gives an age of 443,000 years. Whole rocks give that age, and 1.16 million years. We get potassium argon ages on the olivine from that basalt of over 20 million years and over 46.5 million years. That's minerals from the same rock samples. So why is it that you get these gross ages? By the way, the rubidium-strontium isochron age is 1143 million years. Notice that? Over 1 billion years.
Haven't they taken samples from the lava flows in Hawaii and some of the pyroclastic material from Mount St. Helens and sent it for testing?
Yeah, we'll talk about Mount St. Helens in a minute, yes. And the lead, which is there's two